So now it's our great pleasure to have Samir Murthy from King's College London, who will give us a countdown from 5 to 4 to 3, as you can see on the title. Please go ahead.
Okay, thank you very much for the invitation and for the nice organization of this workshop. Pleasure to give this talk. The main physics question underlying my talk is to account for the statistical origin of black hole entropy. And string theory has been very good at doing this. It's one of the successes of string theory. And as many of you here know, that effort has also led to many connections to modular, modular, automorphic forms of various types. We heard one example in the talk of Boris yesterday. Now, today I want to describe such a connection, but in a slightly different and perhaps broader context, namely that of ADS-CFT, which is a conjecture which relates gravitational theory in 5-dimensional spaces to gauge theories in 4 dimensions. And in this context, I asked the same question, namely, what are the microscopic states of a supersymmetric black hole in the variables of the 4-dimensional gauge theory? Now, this question itself has been around for about 15 years or so. And there's been some new progress in the last 2 or 3 years. This is what I want to discuss today. Everything I talk about, well, most of what I talk about will be joint work with many people, Davide Cassani, Dario Martelli, and mainly Alejandro Cabo Vicet. And then towards the end, also Arash Arabi Ardehali. These two are postdocs with us at King's. And what we find is that the microscopic states of supersymmetric black holes in ADS can be described in terms of an integral over unitary matrices, which arise from 4-dimensional super-Yang theory. And the calculations that I'll describe really begin as some asymptotic developments of certain infinite products. And in doing these calculations, we find relations with, firstly, 3-dimensional Chern-Simons theory. I hope to get to this by the end of the talk, but if I don't have time, then that has to be postponed. But more interestingly, for this audience, relations with functions arising in number theory, most notably a Kronecker-Eisenstein series of the type that we've already seen at least 2 times in this conference, maybe 3 times. And the one I'll talk about has relations with the elliptic dilogarithm of Bloch-Henry. So I'll come to all this. So let me then begin by, as the organizers asked, by just laying out an explicit mathematical problem. So here it is. I've tried to be as precise as possible. Calculate the following n-dimensional integral. Okay. So this integral is a function of tau, which is in the upper half plane. And the variables of integration live in R mod Z. And the integrand is a function of 2 variables. It's actually a specialization of a function of 3 variables called the elliptic gamma function, which has been studied by Felder and Marchenko and Spiridonov and Vartanov. But in this specialization, it's actually much simpler. It looks like this. It's essentially a ratio of McMahon functions with an insertion of another parameter, zeta. Okay, so that's the problem. So the problem is to evaluate this integral. I'll just leave this for a few seconds in case. So the next 20 minutes or so, what I want to do is to explain the physics of this, where this comes from, why this is interesting, and what we expect from physics. But in case you want to zone off, then and you just want to think about this and calculate this, I'll just leave this for a few seconds. And after 20 minutes, if you have any comments, please do let me know. Okay, so then I start with a bit of physics. So the starting point is, so there are 2 ideas from physics that I'll use to set up the main problem. The first one goes back to Bekenstein-Hawking in the 70s, who said that given any black hole, this is a solution of Einstein's equations, which is surrounded by a one-way surface called the event horizon. So given any such solution to Einstein's equations, you can associate to it a thermodynamic entropy, which is equal to the area of that horizon divided by 4 divided by the Newton's constant. Now, combining this with the Boltzmann equation, which says that any thermodynamic entropy must be interpreted as the logarithm of the number of microscopic states of a system, one can associate some integer to every black hole. Okay, so that's the first idea. Of course, this statement is not quite precise. Boltzmann meant this in an asymptotic sense, and I'll try to make this more precise in the context that we have. Okay, but roughly, this is the idea. Given a black hole solution, you can associate some integer number of states to it. Now, to actually understand what these states are, one needs a quantum theory of gravity. And that leads to the second idea, namely the ADS-CFT correspondence, which conjecturally tells you what is the quantum theory of gravity for a type of gravitational theory. So this is a 5-dimensional theory, which is asymptotically ADS. ADS stands for anti-de Sitter. What that means is that there's in the 5 dimensions, there's a radial direction going from 0 to infinity. And near infinity, so asymptotically, the space is a hyperbolic space. Okay? The space of constant negative curvature. And the conjecture relates the quantum theory of gravity on such a space to a gauge theory living on the conformal boundary, the asymptotic boundary of that space. Here I've taken that to be S3 times time. Okay, so this is where the gauge theory lives. And so the picture is supposed to be as follows. So the gauge theory lives on the boundary of this, lives on the sphere. And here I've cut open the sphere, and the gravitational theory is like a solid ball whose boundary is the sphere. Okay, so black holes will live somewhere inside this. Okay, now so this is the prototypical example here. So the gauge theory in question is maximally supersymmetric Yang-Mills theory, n equal to 4 Yang-Mills theory, which is exactly the theory, which is one of the theories we heard just now in Greg's talk. So this has 2 parameters, the rank of the gauge group, and another parameter called the 12 coupling, which is a real positive number. Now, correspondingly, the gravitational theory has 2 parameters, Newton's constant and the inverse radius of curvature of the hyperbolic space in Planck units. And the conjecture starts by giving you a dictionary between the parameters. And lambda here is like an interpolating parameter. So on the gauge theory side, you have perturbation theory in lambda, and on the gravitational side, you have a perturbation theory in 1 over lambda. And this is what makes the conjecture non-trivial and also difficult to check, because you need to calculate. If you want to compare, then you need some quantities, either exact in lambda, or another strategy is to look at observables which are independent of lambda. And that's the kind of thing I'll be doing. These are supersymmetric observables.
Samir, these are string units? Because I don't understand the units otherwise.
In 5-dimensional Planck units.
Ah.
All right. So this is the equation I ask you to remember, that 1 over n squared is g Newton. Very good. Now, we put these 2 ideas together and formulate the main physics question. So this is the same setup as I just described. Now this gravitational theory admits black hole solutions, and in particular, solutions that preserve 2 of the 32 supercharges of the theory. These are called 1/16 ppс black holes. And these are labeled by 1 integer. And the entropy of these black holes are a function of that integer divided by 4 times Newton's constant. And because g Newton is 1 over n squared, if you fix the other quantities appropriately, this scales as n squared becomes large. Okay. Now we want to ask, what is the statistical entropy of these black holes? The natural place to look are the 1/16 BPS states in the Yang-Mills theory. And there is a quantity called the superconformal index, which gets contributions from these states. Okay, so it's defined as a trace over the Hilbert space in Yang-Mills theory of this fixed charge. I'll explain this a little more. And the main question is, and this quantity is protected, it's independent of lambda. So the question is the logarithm of this? So the moral question is, does this index capture the black hole entropy? In other words, is the logarithm of dn equal to the black hole entropy. Okay? And even at a more basic level, does it scale as n squared in the way that the entropy is supposed to scale? Okay. So this question was first formulated and investigated in this very nice paper. And at that time, the answer seemed to be negative. Okay. And then there are many possible sort of subtleties in formulating this question, and I'll discuss a few of them. But in the last few years, there's been new progress, and we've understood that, in fact, not only does this log of the index scale as n squared, but in fact, you get on the nose the black hole entropy including this function. So that's what I want to discuss. And I'll try to get progressively more precise as we go along. So first, what I'll tell you about is a little bit about what this index is, what these black holes are, and what is the meaning of this expectation. Okay. But please do ask questions at any point of time. So for instance, now. All right. So let me then describe what this index is. So any quantum theory comes with a Hilbert space, and that Hilbert space is decomposed in representations of the symmetry algebra of the quantum theory. So n equal to 4 superangles, again, we heard the symmetry algebra of this theory in Greg's talk. Here I'll be using sort of only a few of the generators of the algebra. So time translations, which is R, and a certain U1 symmetry called the R symmetry. This is a subset of the larger R symmetry groups that Greg discussed. And their eigenvalues are called E and R. And the fact that this theory is living on S3 means that there's an SO4 symmetry, and the reps now are labeled by two half integers, J1 and J2. Now, in addition, there is supersymmetry. So again, I won't say very much. Greg explained all this very beautifully. I'll just be very basic. It means that so firstly, that the whole theory has some Z2 grading into bosons and fermions. The grading is called -1 to the F. +1 is bosons, -1 is fermions. And there's a fermionic generator called curly Q, which is complex. So QQ bar anti-commute to this combination of these charges, E, J1, J2, and R. And we focus on states, BPS states, which means that they're annihilated by Q and Q bar, which means that E is completely determined in terms of J and R. So we can just focus on these two charges. And now the rules of the superconformal index of constructing protected quantities. So I won't discuss this, it'll take me another 5 minutes, but I don't want to spend those 5 minutes. The rule is that you should look at charges which commute with the supercharge. Okay. So neither J nor R commutes with Q, but one combination, 2J plus R, actually commutes with the supercharge. So the index is built as follows. It's a trace over the Hilbert space. This is the full Hilbert space of the theory, times -1 to the F, times e to the 2 pi tau. Tau is our tau parameter, times 2J plus R. Okay, so this is the sort of simplest superconformal index to which these 1/16 BPS states contribute. The whole story can be made more complicated, and everything works, but I don't want to discuss any extensions. So this really is sort of a generating function of indices. This in the index, you should think of a Fourier expansion. There's a 3 here for reasons of convention. Physicists will immediately recognize this. This is the fact that the R charge of n equal to 4 superangles theory is quantized in units of 1/3. Okay, so these Dn are the superconformal indices for fixed charge n. N is 2J plus R. This In is also sometimes called the index. So this is the index is a generating function. Sometimes I'll call this the index function, or as in physics, I'll call this the microcanonical index and the canonical index. Okay, they're just related as such. Okay, so that's the superconformal index. Now, let me tell you a little bit about black holes. So the black holes in question are solutions of what is called minimal ADS5 supergravity, which is a theory of the metric and one gauge field. And the charge of this gauge field is precisely this U1R charge that I talked about. And the simplest supersymmetric black hole also has charges J and R, can be labeled by these charges. And in gravity, one often scales out the Newton's constant, n square, and writes gravitational charges small g and small r. Now, these are two charges, but in fact, if you look at this black hole solution in supergravity, you find that those two charges are not independent. There's a relation, which is a little bit complicated, but it's completely explicit. You can write it down. Here I've shown you the nature of that relation. So for large charges, it's something simple. Okay. So in effect, there's only one independent charge, and you can choose that to be 2j plus r as before. And therefore, if you measure the entropy is a function of these charges. There's 1 over g Newton as should be, and times a function of the gravitational charges. And you can write this as n squared times 1 function of the gravitational charge, small n over n squared. Okay. So the black holes, so the summary so far is that the black holes of the type I'm considering are labeled by one integer n, and the entropy is given by one function, and so is the superconformal index, dn of n. And the question of Bacon-Stein-Hawking translates as follows: is log of dn asymptotically equal to the black hole entropy? All right. Now let me. So this entropy is some specific function. Again, it's a little bit. The formula is a bit complicated, but it's completely explicit. Here I show you. That's the right-hand x-axis is the charge. The y-axis is the formula for the entropy. And here you see the sort of 2/3 growth of the entropy. And in this direction, you also see the n square growth of the entropy. All right. Now, what does this asymptotic condition mean? So there are two limits which people discuss. So the first one is what comes from physics. It's called the large N limit, which means that the charge and the rank of the gauge group both go to infinity, with the gravitational charge being fixed, n over n square being fixed. Mathematically, this is more subtle to define because you're sort of changing theories and changing the charge at the same time. One has to ask whether there is such a limit and so on. There's another limit which people discuss, and this is sort of much easier to define mathematically. It's called the Cardy-like limit. Namely, you just fix n. So n, remember, is the rank of the gauge group. So you work in SU2, SU3, whatever you want, and then just take the charge to infinity, and you ask whether asymptotically this equation holds. Okay, so that's neither of these two limits are subsets of each other. They're completely different limits. There's a regime of overlap when both the charge and the ratio is very large. Okay, this is the regime when the black hole becomes very large and sort of fills up area space, so to speak. Okay, any questions so far? Very good. So then the next thing I want to discuss is the following. So in number theory and in many parts of, in combinatorics, in many parts of mathematics, when you have a sequence of such integers, so the rule of thumb is to sort of make them into a generating function and study the properties of that function. Okay. But in fact, in physics also, this principle is very well understood, and it's been understood for more than, this principle operates for more than 100 years, even in thermodynamics, and in physics we call it the change of ensemble. Okay. So these will be called microcanonical ensemble, but in fact, even 100 years ago, people were not studying of gases with fixed energy. We were fixing the temperature and then asking what happens to the microscopic phase of the gas. Okay, that's called the canonical ensemble. And in gravitational thermodynamics, black hole thermodynamics, Gibbons and Hawking explained what that, how to go between these two ensembles. Okay, so if you have a sequence of integers, you literally just take the sum. Here it's slightly more complicated. If you're given a black hole solution, you're supposed to look at some the on-shell action of the areas. Okay, so I won't discuss this, but I want to say that for supersymmetric black holes, this procedure turns out to be singular. There's a subtlety. So this is a physics slide, but I want to say it. It's singular. Singular because the supersymmetric black holes have an infinite throat deep inside the ADS, and one has to regularize. And that's what we did in this paper. And what we found is that, so you do the regularization as follows. You keep the condition of supersymmetry manifest, you go away from extremality, and there you have well-defined sort of finite horizon geometries. So this is what you expect.
Sorry, Samir, could you say more about what the throat is? The throat is at the horizon, is that right?
Yeah, so let me say it properly. So you take the ADS black hole solution, right? So if you have a thermal black hole, then you look at the Euclidean solution, then you'll get some cigar geometry. Okay, so there's some infinity coming from the asymptotics of ADS that you have to subtract, let's say, with background subtraction or something like that. For supersymmetric black holes, there's another infinity coming from the fact that as you go near the throat of the black hole, because it's supersymmetric, you don't get a cigar, you just get an infinite cylinder, okay, in the infrared. Is that clear?
How did you go from the cylinder to the cigar?
So here, you mean in this picture. So let me explain this picture. So the black hole is living here, that's the cylinder. Now it turns out that there is actually a 4-parameter family of solutions, of which this black hole is sort of a codimension 2 object. So what we do is, if you look at solutions and you impose supersymmetry, but not extremality, then you still get good solutions to the theory. These are not good Lorentzian solutions, they have closed time-like curves. But in the Euclidean theory, they're perfectly well defined. They are cigar-like solutions. They're not extremal, that's why you have a cigar-like object.
I see, okay.
You go here, and then the Gibbons-Hawking procedure is fine. You can just calculate the on-shell action as usual, it's finite after the usual regularization. And then you take a limit towards the black hole. So that's what was spelled out in this paper. And when you do that, what you find is that, in fact, the action is independent of beta. Okay. And therefore, you can just read off what is the canonical free energy of the black hole. Okay. So I've translated to units of n and tau, and it's pi I over 27n square times 2 tau plus 1 cube divided by tau square. Okay, this is a function which will appear again and again. So I'll try to remember it. It's n square times a cubic divided by quadratic. There's more to say here. This picture also, so for the physicists, this picture also says why the supersymmetric black hole actually contributes to the index. So there's these kind of questions. I don't want to get into that now, but maybe you can ask me after the talk if you have questions. All right, so that's the status. So this was about 2 years ago, and after that, there were many, many developments, and which is what I want to discuss. So in going to the canonical ensemble, you've actually done 2 things. Firstly, you've simplified the problem. So instead of looking at the sequence of integers and asking whether it's asymptotically equal to the entropy, you look at the generating function of the index, canonical index, and the translation is simply whether the log of this function of tau equals this function that I just showed you, n squared over 27 pi I 2 tau plus 1 cube divided by tau square. And the 2 limits that I showed you have a translation. So the Cardi-like limit is you fix the rank n and just take tau to 0. The large n limit is more subtle. I'll just say something here and come back to this after some time. So you essentially fix tau and take n to infinity. So again, it's not mathematically obvious that this is a well-defined limit, but in physics, we expect that there is such a limit, although we don't have a formula for it, even conjecture. Okay. So now this is what I want to deal with. So all this was sort of a physics background to set up this problem. What I want to do now is to focus. So the main player of the talk will be this function. So it's the function I showed you on the first slide. And I want to analyze that function. And this is the expectation from physics. Notice already that whatever this function is, it's not a holomorphic modular form under SL2Z, because such things near tau goes to 0 have a 1 over tau and not a 1 over tau square behavior. All right. So let me now describe what this superconformal index is. Again, unless there are other questions, let me just pause for a few seconds. All right. So this index begins its life as an integral over unitary matrices of size n. Okay, n by n unitary matrices U, of an exponential of an infinite series. Each term in the series looks like trace u to the n, trace u dagger to the n, and the series is controlled by one function, which is this explicit function I've called here. It's called the single particle index. Okay. Now again, this is well known. Why this is the correct counting function, I don't want to discuss. It's fairly standard. Just to give you some sense of it, This F, so this gauge theory is made up of gauge invariant words. So there's a Lagrangian, and there are letters which are the fields of the theory, and you're supposed to put them together and count how many operators there are. This F roughly counts how many operators contribute to this index, how many letters contribute to this index, called the single letter trace. This exponential essentially makes beads and necklaces of these words, of the letters, and makes words. So that's a standard combinatorial problem. And then the integral over the group projects you onto the gauge invariant. So this is like fairly standard basic invariant theory. Okay, or you can understand this using supersymmetric localization. Anyway, I'm going to take this as a given. And now, what do we do? So what we're taught to do when faced with such an integral over matrices is you first diagonalize the matrix. These are the eigenvalues. The small ui I'm going to call eigenphases or eigenangles. And this Haar measure on the group, you write in terms of the flat measure of these eigenphases. And then you'll get some van der Monde determinant, which you can exponentiate, and you'll get some big action of this type. Now, the van der Monde determinant is only a function of the differences of the eigenphases. That's a familiar fact. This matrix model has a particular feature that even the original action itself is a double trace, and therefore the whole action is a sum over pairs of interactions. If I think of the eigenvalues as some particles, there's a potential which depends only on the distance between the two particles, ui minus uj, and it's summed over all pairs of particles. This is some constant which is not going to affect most of the considerations. Okay.
Samir, can I
Yes.
ask you a question? So it isn't obvious to me that this thing has a Fourier expansion in tau.
Not yet. You'll see it in one slide. So just hold your horses for 1 minute. So here it is. So if you actually calculate this f, okay, this infinite series turns into an infinite product because of the exponential, and then you can just calculate it, and you'll see that that becomes exactly what I showed you on the first slide. And now you can see that the gamma function is periodic in Z with period 1, because it only depends on zeta. Sorry, I should have said this again. Q is e to the 2 pi r tau, zeta is e to the 2 pi r z. So this is periodic in Z with period 1. And because there's a 2/3 here, the whole integral is periodic in tau with period 3. Yeah?
Thank you.
All right. Okay, so that's the end of the physics introduction. How am I doing with time? Okay. So in the next half and a little bit of the talk, what I want to discuss is I want to discuss this integral. So now it's a completely explicit integral, and show that it indeed obeys the expectations that we have from physics, and then analyze it a little more. So the first thing I want to say is that for a fixed n, this is a completely explicit function. So one can just study it on the computer and ask whether the expectation is at least roughly satisfied. And this is what it looks like. Okay. So what I've plotted here is for various ranks. So this is UN gauge group, start U2, U3 up to U10. And the solid lines are the black hole entropy formula for that rank. Okay, this is my expectation. And the dots are the logarithm of the absolute value of the index for a given charge. The horizontal axis is the charge. Okay, and you see many things here. So the first thing to see is that by and large, there's a very good agreement with what is expected. Okay, so the baseline is established. Now you can sort of try to do more sophisticated experiments. So firstly here, notice that I plotted the absolute value, which is not what you should really do. But if I actually plotted D, I would have some enormous oscillations. And once I've established this baseline, I can divide by it. I won't show you the numerical experiments, but already with this plot, you can see lots of patterns. So one pattern you can see, at least for which becomes clearer at higher n, is there's this oscillation. Okay, so here it's most clear. There's oscillation, which is, at least to the naked eye, is periodic. And then there is this sort of dive down towards negative infinity. And that's really a sign that you should plot it in a better way. That's because I'm plotting a log, and that looks like a log of 0. That's exactly what is happening. Okay. So what I want to do now is to sort of explain. So I won't explain everything about these graphs, but what I want to explain is at least the rough behavior and a little bit about these oscillations. There's another interesting feature here at low charges. There is not an oscillation. It looks different. That also I can explain, but I won't have time to do that. You can ask me after that. Okay, so now I'm going to switch to my iPad. Which is to stop here. So in the meantime, you can ask me questions. Share, airplay, share. Mirroring and zoom. Okay, do you see this?
Yeah.
Perfect. Okay, so let me start again. I've just written down the definition. So that's the superconformal index as an integral over these n parameters ui. Okay, so this is this elliptic gamma function. And so this was already asked. So this is periodic with period 1, and therefore the index is periodic with period 3. Okay, so that's the Fourier expansion like I showed you. So first, actually, let me tell you a little bit about these microcanonical indices. So if I want to describe, so let me just calculate this. So that this, I just invert this formula, so it's an inverse Fourier transform, like so. Okay, and I want to start to calculate this. Right. Now, if I want to calculate it, the natural thing, so first I want to ask what happens when the charge becomes very large and goes to infinity. So the instinct is to do some kind of a saddle point approximation. And that so when n goes to infinity, we'll say that tau goes to 0 in the saddle point. But in fact, if you think about it a little bit, what really goes to 0 is the imaginary part of tau, not just tau, because the way things are here. And the real part of tau can be any rational number. Oops. Okay. It has to be rational because sort of you want a good asymptotic limit. So let me focus on that a little bit and explain what is the. Let me just explain a little bit what this real part of tau is doing. It's very elementary what I'm going to say, but it's a bit important, so I'll say it. So suppose you have a Q series of this type. Okay, so f of Q is some df of n q to the n, and I want to ask what is df of n. So df of n. So now I've gone to the variable q, which is e to the 2 pi tau. So df of n is written as a contour integral of the following sort. So f of q is sort of well defined. Let's say it's a holomorphic function in the unit disk, and near the sort of on the unit circle, there might be some singularities. That's typically what happens. So you write this contour integral. So this contour is some arbitrary contour inside the unit disk. And then you ask, you take this contour and you sort of take it towards the unit disk and make it go towards a singularity. So many times, for instance, the dominant singularity is at tau equal to 0 at q equal to 1. And then the sort of dominant part of the integral comes from this part of the contour. Okay, this is a standard circle method. And I think in this conference, everybody knows this very, very well. So if you take, for instance, 1 over e of tau, you get the near tau goes to 0. The behavior is singular indeed. It goes like so. And then the saddle point value of this, you have to take this. So it's the following integral is some Bessel function, which then you can further write down some asymptotic expansion of the following tau. Okay, so this is completely standard. What I want to say is that the saddle lives somewhere here. Okay, so it somewhere very close to 1. So tau equal to 0, and looks like this as n goes to infinity. Now, suppose you have a different example. Suppose you say, I define a function g, which is the same as f, except that tau is shifted by tau plus half. Okay, so I change the real part of tau, and then write a Fourier expansion as before. Then all I've done is to take the same function and sort of rotate it in the Q plane by half. So now the dominant singularity is over there, and the saddle point now is half plus what used to be the saddle point. Okay, so all this is completely elementary. Now, if I compare f and g, let's see what is happening. So firstly, the values of the Fourier coefficients only differ in phase, okay, because of the shift of half. The imaginary part of the saddle point values are the same. The real parts are shifted by half. And so the real part of the saddle point absorbs this phase oscillation. Okay. So the new function g has a dominant growth at some other point over here. And if you now, for g, if you look over there, the old saddle point, you'll find some subdominant growth. Okay. And as an extreme example of this, you can do the following exercise. So take θ3 and θ4, the Jacobi theta functions and their inverses, and you'll see that as tau goes to 0, log of f has a dominant singularity, but log of g, so f and g here are related exactly like as I discussed up here. Log of f has a dominant singularity at tau goes to 0, but log of g not only has a subdominant, in fact, it doesn't grow at all. There's no growth at all at tau goes to 0. Okay, so that's an instructive example. So now let's look at this black hole function that we want, this in of tau. And as it turns out, it's of this type. So near tau equal to 0, there is actually no growth at all. And the dominant growth comes at the other two cube roots of unity. Okay. And so that's the picture. And now if I want to study, so that this is really where the black hole is defined. And if I want to study it, then I have to sort of go here and then zoom in. So I'm back to the variables where the period is 3. So I go to tau goes to tau plus 1 to reach the cube root, and then I change variables and then call it tau goes to 0. Okay. So now what I want to do is to study these gamma functions, elliptic gamma functions near tau goes to 0. I can do that, and using the Euler-Maclaurin formula, you can write down what the asymptotics are. And it turns out that it starts with 1 over tau square, then there's a 1 over tau and O of 1. And the coefficients are what are called periodic Bernoulli polynomials. So I used, by the way, an exposition of this due to Don Zagier, which I found very nice and instructive in one of his papers. Bn is the periodic Bernoulli polynomial. This is just, one way of defining it is you take the Bernoulli polynomial and take the real part of z in between 0 and 1, and then translate by periodicity. In other words, you just write down the Fourier expansion and define it using that. Okay, so now that I have that, I can just plot what this potential is. I can just write down in the same asymptotic limit what this potential is, and I get some piecewise polynomial function of this type. And now it's very easy to see where the saddle points are between between these two limits. The saddle points essentially are here. So all these things, all these variables, want to condense over there, and then you can read off what the potential is. Okay, so it was very fast, but these are elementary calculations, and that's what we did in this paper, again with Alejandro Cabo Bisset, Davide Cassani, and Dario Martelli. And then there are also other papers by one by Kim and Song, which essentially did the same calculation. What one finds is the following. So you get that the log, so I should have said something. So you use the saddle point calculation, and then essentially you can do the integral after using the saddle point value. Oops, now this froze. Sorry, what, Axel, what are you seeing on the screen?
It's still the graph of the
graph.
potential. Yeah.
Then is it moving now?
No.
I was afraid of this, but in fact, I've more or less finished. There it is.
No, it's moving. Yeah.
Good. All right. So what you find is exactly pi n square over 27 times 1 over tau square plus.
Sorry, now it disappeared.
Whoa. I'll try again. Otherwise, I'll join by Zoom as one of you taught me. So let me maybe stop share. Sorry about that. I'll try once more and then. All right. I hope I'm back.
Yeah, it's working again.
Okay, so if this goes away, then I'll join my Zoom. And here you can see that it's very easy to see that this is equal to 1 plus 2 tau cube divided by tau square plus O of 1. So that's equal to F grav of tau. Okay, so indeed, the leading singularities are exactly that, as expected from gravity. Okay. In fact, this technique, you can, this Euler-Maclaurin formula, you can also calculate the complete asymptotic expansion. I'll come back to this. But for the moment, I wanted to show that you get this agreement. And now, if you want to calculate these degeneracies, you plug in this asymptotic value, and then you extremize. And because this is a cubic function, find that the saddle point value is some cube root. And because tau has to be in the upper half plane, one important point is that the correct value of tau is something like that. So oftentimes in these problems, in the simpler problems, you find tau coming in directly from the on the imaginary axis, and here you don't. And that reflects itself in the fact that when you put it back, the contribution of the saddle point to these degeneracies in the exponent has a real part, that's the black hole entropy. But there's also an imaginary part, which is not 0. So what does that mean? Well, you have to add the other cusps. And as I said, there is this sort of complex conjugate cusp, which is not seen in this analysis if you only zoom in at this point. But if you do that as well and add it, then indeed what you get is that the degeneracy looks like the black hole entropy times the cosine of something. And these are exactly the oscillations that you showed. So I showed the log of that. And that's exactly what is happening. Okay.
But the other cusp doesn't have a black hole, a geometrical interpretation?
That's a very good question. Let me pause on this question. I want to say a little more than this. Please ask this after 10 minutes. So now recall that, so you had two cusps, but in fact, there are, in the problem, you can expect many cusps. So both from the physics side of it, because you can have other asymptotically area solutions, also from mathematics, because you can ask what happens at the other rational points. Okay. So that's what I want to answer now. I'll stop sharing again and get back to my computer.
So you have about 15 minutes left, by the way.
Thanks. Except that I lost my, sorry. Here it is. Share. There it is. Okay, can you see it?
Mm-hmm. Yeah.
All right, great. So, so one thing one can do is to do a similar asymptotic expansion at all cusps, but I want to show you something else, another method to talk about the other cusps. So this is a Largian limit. So I get back to this matrix model. So and now this what I'm going to say next is collaboration with Alejandro Cabo Bisset. And what we said is, well, let's try to solve this matrix model, like was taught to us by Brezin, Six, and Parisian Zuber, the Largian methods. So the idea is that you try to find, so because this action has a sum of n squared terms, when n squared becomes large, you can just try to look at the variational problem, variational critical points of V, and that gives a good estimate for the integral. And one expects something like this. Okay, so it's a sum over saddle points, and that's also nice to sort of match to gravity. Now the problem is that is what I mentioned earlier, that usually in this Brezin, Six, and Parisi-Zuber matrix integrals, one has not just a two-particle interaction, but a one-particle interaction. So these eigenvalues want to condense somewhere, and then the two-particle repulsion due to van der Waal sort of spreads out the eigenvalues into some branch cut in the complex plane. So this is the classic thing we've learned. Here there is no local minimum. So if U is defined on a circle, you have only a two-particle interaction, then the critical distribution that you will imagine is the uniform distribution around the circle. If you calculate what the entropy of that is, you get 0. Okay, this is what was done in the old papers. But another subtlety about this matrix model is that the coupling constant is also complex. Okay, so you can see this both, as I just showed you, tau should have both a real and an imaginary part. So here, real would mean that tau is purely imaginary, but as I just showed you, the real part of tau is also important. Okay, and our idea was that, well, maybe both these problems sort of play off against each other, and we should look for complex saddle points. Okay, so this is the U plane. This is not the U plane that Greg talked about. The U just being these eigenphases I discussed, and this here is the original regime of definition of the integral. But when U becomes complex, there's another mark point called tau, which is equally natural. And if I had a periodic function, then I would imagine that instead of a uniform distribution on this cycle, I could also have a uniform distribution on this cycle, and in fact, along any lattice point. Okay, so there's an infinite family of saddles labeled by the lattice points, or I can equally well say it on the torus. The problem is now well defined on the torus, and you can ask Mn is some winding number. And what we find is that roughly this thing works. There's something of the sort that works, and the entropy of this uniform distribution of the A cycle gives you the entropy of pure ADS, while the entropy of the uniform distribution of the B cycle gives you really on the nose the ADS black hole entropy. Okay, so now let me explain this a little bit. So let's start with a lemma. It says that it's the same situation that I have. You have these two-particle interactions. And suppose you have a potential which is even and periodic, and tau could be a period which is complex. And you want to solve the variational equations. I've written both holomorphic and anti-holomorphic because V is not necessarily holomorphic. Okay? It's periodic. In the lemma, so the uniform distribution along the period is a solution along the line stretching between 0 and t, the solution of the variational equations. Okay, that was our intuition, and you can check this in 2 or 3 lines. The second part of the lemma is that the action of the distribution is the average value of V along this distribution. Okay, that's also easy to check in 2 or 3 lines. Now, the fact that the
sorry, that depends very much on the particular form of V, right? It's
not this fact. This fact is always true for any.
Oh, no, number 1.
No, so anything, both
any V, any V,
obeying these conditions, and S is only a two-particle condition. Okay. If it's periodic with a complex period, the only thing we use is the V is periodic and even. I can explain this to you later. What is not obvious in this setup is that because V is not holomorphic, it's not obvious why the contour deformation works. Okay. And for that, you need a separate argument. We had this in the paper at large N, and I want to make a sort of comment on this again. But sorry, this is, let me see, why is Greg confused? All I use is that it's important that the potential is purely of the two-particle type. Of course, it's not true if there's a single particle potential. That's the main point which goes into this. But if it's a sum over all two-particle pairs, and it's periodic, then in the variational equation, then essentially when you sum over all pairs, you just get 0. That's roughly what goes into this. Let me continue, and maybe you can ask me again later. Okay, now the problem is that our potential is not periodic. Okay, so it's only quasi-periodic. So in the X direction, it's completely periodic. In the Y direction, the lack of periodicity is blocked by the function theta 0, which is the Jacobi theta function divided by the Dedekind eta function. Okay, so now what do we do? Well, we do a deformation. So we construct a function called Q, which, so Z here is Z. So I've decomposed Z along the torus directions 1 and tau, Z1 and Z2. And notice here that these things, this is a Bernoulli polynomial of Z2, and this is theta 0 to the power Z2. So this is explicitly not meromorphic. But when Z2 is 0 on the original contour of definition, Q is equal to 1 over gamma. Okay, so that's why it's a deformation. It's the original problem we're not changing. And now this function has the following properties. The absolute value of Q is doubly periodic. Z goes to Z plus 1 and Z goes to Z plus tau. And the sort of interesting statement is that minus tau 2 is the imaginary part of tau. Tau 2 times log of the absolute value of Q is this particular Kronecker Eisenstein series. Okay, it's the imaginary part of this Kronecker Eisenstein series. Okay, so this notation I've borrowed from Zagier's paper on this, and this particular Kronecker Eisenstein series is has been studied intensively by mathematicians because it's equal to what is called the elliptic dilogarithm studied by Bloch and Wigner. Okay. For us, at the moment, the only thing I want to use is that there's an explicit Fourier expansion along both directions that's just given by this formula. I can just read it off. And therefore, you can, so once we extend the Super-Yang-Mills action as this, you just, by the lemma, you just get a family of saddles labeled by any lattice point, and the action of the saddle, which is the average value of the potential, is now very easy to calculate because the Fourier series is given to you. So the average value is again a 3-line calculation. You just use the Fourier series and read off the appropriate Fourier coefficient. Okay. So before I present the result, I want to just say one remark which is slightly parenthetical, which is to hook back to this equation. This equation that I showed you here, over here, is actually the imaginary part of a nicer equation, which is like this. Okay, it says that this Bloch-Wigner function is actually the period function. And here, so this is, so log Q minus its modular transformation on the left-hand side. Okay. And I want to say that there's actually an analogous formula for, sorry, this should have been absolute Q here. By absolute Q, replaced by the actual elliptic, the holomorphic elliptic gamma function. And this formula is some kind of a single valued version of that formula, which I'm not showing you. This is work in progress with Stavros Garoufalidis and Don Zagier, which in turn is connected to a notion of what is called holomorphic quantum modular forms, for which I refer to you to Don's talk. Okay. So this whole thing is a bit parenthetical, but I want to say that this formula, which I've not shown you, can be used to sort of get around this and indirectly write a holomorphic argument, at least to all orders in perturbation theory. So now I want to show you the results. So the result is, by the result, I mean, I want to calculate the effective action at any saddle point, Mn. And as I said, the calculation is easy. The answer is also easy. It's just in terms of m tau plus n, it's just 2 times that plus a Dirichlet character cube divided by m tau plus n square divided by m. And for mn equal to 0, this is exactly the free energy of the black hole. So now we can play the following game. Say you fix yourself at some point in tau. Okay, so over here, say, and you ask of all these phases, whose real part is maximum? So which dominates? Okay, because you're looking at the contribution to the full functional integral. You find that for large values of imaginary tau, it's just the 0-1 saddle, the pure ADS, that dominates. As we go towards tau equal to 0, the black hole starts to dominate, as you can see here. And this is this other complex conjugate solution that I described. Okay, so this at least partially answers Greg's question. There is another phase, not yet about the physical interpretation, but there is this phase. Here I've cut off the imaginary tau at 0.1. But now notice that if tau goes towards the rational point, then the Mn saddle, that particular rational point, will start to dominate. If you go further down, like so, here tau goes to, imaginary tau goes to 0.01, you'll see that near every rational point, there is a new phase that is dominating, and there are these phase boundaries that you can count. Okay. Now, I have 5 minutes, is that right? Okay. So then I want to say, so let me just pause for any question about this. So that's the phase structure that we have. I'll just make some comments. So I want to write a formula like this. What do I mean by the symbol? So I don't have it, certainly not an exact formula. But in fact, I don't even have a classification of all saddle points. That's not the claim. What this formula means is that if tau goes near any of the rational points, then this expression gives you the complete asymptotic expansion at that point, okay, at the rational point. That's what this formula means. Now, if you take n square really going to infinity, and if there are no other saddle points, then if you're in one of these chambers, then the contribution from any other chamber goes to 0 exponentially as n square goes to infinity. And therefore, the only tau dependence remaining is the chamber dependence. Okay, so that's a comment. And all this, like, this was sort of using lots of methods and some intuition. Instead, you can just ask, okay, can I just directly study the Cardi-like asymptotics? And you can. I'll show you this in a second. I want to discuss a little bit of physics about this older paper of Greg and collaborators. I'll not do this, I'll postpone this. Sorry, there was a question by Greg, so let me just explain. Let me give you one sentence answer. The answer is that, in fact, so the prediction from our work is that there's a family of gravitational solutions. And from this old paper of yours and others, the expectation is that these might be orbifolds of the black hole. And something like that has been borne out in this very recent paper of these people. Okay, so I'm happy to discuss more about this again. Now, this is my last slide. So now if you want to be a little more rigorous, you can just say, okay, forget about these large N methods. Just go back to the Cardi-like problem, fix yourself to some rank N, and ask, can you calculate the complete perturbation expansion? And these methods that I showed you, the Euler-Maclaurin, you can actually just use that to form a complete, to develop the full asymptotics. And the surprise from that point of view is that the expansion indeed terminates at linear order. So it starts with 1 over tau square. There's a 1 over tau, there's a 1, and tau and nothing else. Okay, exactly as predicted from this other analysis. So this method has the advantage that you really have everything under control for even finite n. And the answer is that the asymptotic expansion near any rational point minus n over m looks like this. There is this function that I just showed you, the effective action. And you also have control. So one disadvantage of this large N method is that the O of one term, the imaginary part of the O of one term, you don't have control. And that can be fixed here. And there's a bit of a surprise that at every rational point, you find that this number is the partition function of Chern-Simons theory of rank n and level plus or minus n on S3 quotient by Zm. Okay, so when this is 1 over m, for instance, you really get a length space. Okay, and then there is another surprise that every term on this right-hand side can be interpreted in terms of three-dimensional Chern-Simons theory. Not just the constant term, but even these divergent terms can be interpreted in terms of three-dimensional Chern-Simons theory. Okay, so I won't have time to explain that, but again, I'm happy to take questions. I want to stop now. Thank you very much for your attention.
Thank you very much, Samir. This was a very nice talk. Are there any questions?
Can you say a little bit more about the last line, please?
I think Greg raised a hand
Oh,
before.
okay, that's right. Yeah, Greg, please just go ahead. Yeah.
Samir, could you please explain more about the connection to Chern-Simons theory, which seems interesting and interesting?
Okay, I think this was also Shara's. So this is a physics. Sorry, let me just see where it is. There's a bunch of things. Here it is. Okay, so. Okay. So the story is as follows. So you remember, so I'm going to use physics language. We start, so you want to calculate some functional integral on S3 times S1. Okay. So the idea is you ask, what happens when the circle size shrinks to 0? And you would expect, based on effective field theory, that there is some description in terms of three-dimensional theories. Now, what we do is, so how do we calculate this effective description? So you say, first you write down all possible terms that can be written down consistent with the symmetries. And that was given to us in these papers. So this was for general bosonic theories, and this was the supersymmetric analog. So, and the statement is that so there's a complete set of terms known, and all of them are essentially supersymmetric completions of some or the other Chern-Simons terms. I have to explain that a little more. When you look at this gauge theory on S3 times S1, what you find, in order to preserve supersymmetry, is that you have to turn on some kind of backgrounds to support the supersymmetry. These backgrounds can be interpreted as a rigid supergravity. Okay? So there's some gauge fields and metric in the background supergravity, as well as your dynamical fields. And the effective Chern-Simons theory and its supersymmetric completion involves both the background and the dynamical fields. Okay, that's just your theory. That's what you would do if you just did the physics correctly. So that's what we did here. There was also a parallel paper on the same day. And now you have to calculate the coefficients of these effective actions. That coefficient, in general, is not easy to calculate, but the fact that every term contains at least one Chern-Simons term means that you can use the fact that it's one loop exact and explicitly calculate a recoupling. So what you have to do is to integrate out all the Kaluza-Klein modes. You get some infinite sum. You have to regulate that. You can do it, and what you find is you get exactly these functions that I showed you. And the story is roughly that the background terms give you the singular pieces in this asymptotic expansion. This is the sort of main new point in physics, that you can account for this 5-dimensional black hole entropy directly starting from a 3-dimensional Chern-Simons calculation. The dynamical terms gives you this constant piece. And then there's this Casimir energy, because there's an issue between path integral and Hamiltonian index, and that gives you the linear piece. So everything really fits together perfectly, as you would imagine.
So I think there was one other short question maybe by Shariar.
I think it was the same, but
It was, thank you. It was the same. I wasn't looking at the participant list, so sorry, Greg. But I can ask, I mean, the question related to Greg's talk as well. And where does this R symmetry come from? So this is not manifest in a classical picture, right? It's just it's an artifact of supersymmetry, and only shows up at the quantum level. Or?
The supersymmetric n equal to 4
yeah.
Yang-Mills theory has an R symmetry. It's you can the Lagrangian.
So I remember you showed n equal to 2-star supersymmetry algebra. And
sorry, you're asking a question to Greg.
No, not to you. I mean anyone. But if can you just elaborate what is the origin of R symmetry? Where does it?
So the theory I'm talking about has, let's say, so you can even talk about the minimal supersymmetric theory where there is one fermion, or the one I have has 4 fermions in.
Yeah, that's it. Yeah.
And the R symmetry just rotates the 4 fermion. There's an SU4 which rotates the 4 fermions, and I've taken a U1 of that SU4.
Okay, so if it was n equal to 2, then you would have SU2. You would have
SU2 times U1, yeah. Or U2, I forget. My Greg can answer this better. But yeah.
the rank of the R symmetry algebra equals the number of supercharges you have in your theory. That's
essentially.
Okay, so maybe this is also a good moment to end the official.
Actually, Axel, I'd like to ask one more question if I could.
Sure, go ahead.
Go to a breakout room, so I can't go to Samir's breakout room.
Yeah, I had the same problem. I wanted to be in your breakout room. Okay.
Yeah. So if I could just ask that question, because I can't go to his breakout room. But you have this, so actually 2 questions, if I may. So there was an imaginary part of that effective action, which really surprised me. Of course, you add them up and you get a real answer. Imaginary part of the saddle point action.
That's right.
Yeah, what does that mean? Is that some kind of, is there an interpretation in terms of some instability?
In terms of what?
Instability?
Instability. No, I don't think so. I think all it's saying is that, so there's this infinite number of saddle points, Mn, and there are 2 of them which dominate equally. So they both have the same real part, but equal and opposite phases. So you're asking a question about the mathematics for the physics.
I guess I'm asking more a question about the general relativity.
Okay, about the physics.
That saddle point, if the imaginary point, a part of the saddle point action indicates there's some kind of instability.
That's a good question. I don't know. It could be that there is a Euclidean solution which connects these 2 actions. I don't know. I'm speculating here. That's a very good question. I don't know the answer to this. So my feeling is that there might be some instanton-like object which might interpolate.
Okay, that's pretty cool.
But I don't know at all. This is a pure.
Okay. Yeah, I got it. So let me ask the other question quickly. So your final result, this amazing result where you get the Chern-Simons action, could you flip that? Yeah, there. Good. So the Chern-Simons partition function on lens spaces can vanish sometimes. I'm wondering what in the world that would mean. Oh, that you have to do PQ lens spaces and you're doing 1M.
Yeah, so I should say,
I'm not sure. I know that Chern-Simons partition functions on lens spaces can and do vanish. And that would look kind of funny for this formula.
I agree. So let me make 2 comments. Firstly, so this is a Zm orbifold where for 1, m, it's a lens space, and otherwise it's, I don't know what to call it. I don't think it's the Mn lens space. And the other comment is that, firstly, so the 1.5 comment is that I think I didn't even know about this, but the second comment is that here there is also a certain Dirichlet character which sometimes appears, which can, for 1, 0, this is 1, and for the other saddle point is -1, but sometimes it can be 0. So for instance, at tau equal to 0, the action completely vanished. So I wonder if what you're saying is related to this. Is there a condition on P and Q when it vanishes?
I don't remember the exact condition. It's in a paper of Dan Fried and Robert Gumpf.
I'll have a look at that. Where
they did numerical evaluation. They did explicit evaluations of Chern-Simons partition functions for lens spaces.
I'll have a look at that.
They discovered this interesting point.
So Greg, your hand is still up. Do you have another question?
No, I'm done. I'll take my hand in.
Okay. Okay, so maybe now we can go to the breakout rooms. There will be several, 5 again, I think. And yeah, if I can ask the speakers as anticipated to go to separate rooms, that would be much appreciated. But first, let's thank Samir again for the very nice talk.
Thank you.
Thank you.
Yeah, so I just opened the 5 rooms.